As an application of the proposition number 3, let us compare the random variable x with its conditional expectation. So we have x and its conditional expectation, x given f. What we do now is that we're going to take the variance of both terms, and we take the difference. Let's compute this difference. This is equal to and now let us look at these 4 terms. A quick observation is that
the law of total expectation.
By the law of total, this term is equal to just e of x. So this part and this part will cancel out. The terms left are ex squared minus e of ex given f squared. Now we are going to play a small trick in here. We subtract and add the second term. And we look at the term in the middle. And we observe that the conditional expectation of x given f is f measurable. So we can insert e of x given f into another e of x given f. You might be confused what I'm talking about. Let me show you. I claim that this part is actually equal to e of x times e of x given f given f. We're pushing one of those two guys in this product, in this square, into the other. Hope you can see that they're actually equal. This simply follows from the fact that this conditional expectation is f measurable. And we are using the property that the conditional expectation of the product xy given f is equal to y times x given f if y is f measurable. We are using this property of conditional expectation. And of course, we are assuming everything here is integrable. So those notations should make sense. So now let's continue. And now, what is this term? And now let us copy everything we have derived so far. We have obtained here we have 1, 2, and 3. 3 is. Now, what is the thing in the middle? If you think of this guy,
the law of total
as a
expectation,
whole, then we have a perfect situation of using which yields just the conditional expectation of x times E of x given f.
the law of total expectation.
Now let's copy everything down. So this part follows from, I told you we're going to have an application of our proposition number 3 here. So now let me show you the application. We're going to show you that under some special hypothesis, we can have a bound for this covariance loss. The setting is as follows. Omega AP probability space as 0. Let x be a random variable whose range is the interval from -1 to 1, or more generally, some bounded interval. For convenience, let us just consider the interval from -1 to 1, namely x is bounded by 1. What we are going to do is that we are going to decompose this interval from -1 to 1 into n subintervals of length 2 over n each. Length 2 over n each. Specifically, we get -1 to 1 written as a union, a disjoint union. And let us give them names. Call this I1, this I2, this In. And now, let f sub k denote the inverse and the x of I sub k for k equal to 1, 2, all the way to n. Then you can easily see that the whole space omega is the disjoint union of f1, f2, all the way to fn. And clearly, f sub k is in A for any k, because fk is the inverse of ik, a Borel subset under the random variable x. So now you can see how we're going to apply the proposition number 3 in here. by applying proposition number 3, we get the conditional expectation of x given f is equal to the summation from k equals 1 to n of the conditional expectation with respect to those sub-sigma algebra f sub k's, where each f sub k is sigma of f sub k times the indicator function f sub k. And this is further equal to the average of x over fk times the indicator function on f sub k, given the probability of each f sub k is non-trivial. But if f sub k is indeed trivial, say if some fk is equal to 0, in that case, this term could vanish. Because remember, in measure theory, we can always ignore the functions defined on the set of measure 0. The sets of measure 0 are always negligible. So we can just forget about it if the probability of that f sub k is indeed 0. So you can think that this guy holds even if some p of fk is indeed 0, with the convention that in that case, this whole term can be ignored. But anyway, recall that this guy is equal to the average of x over the domain f sub k. And because on f sub k, by our definition, x is in some interval I sub k. So it has a minimum and maximum, some interval like this. Let's call it alpha comma beta. So this integral must be bounded above by the supremum of ik, while bounded below by the infimum of ik. And this tells us for any omega in f sub k, E of x given f evaluated at omega is in the closure of the interval I sub k. And in particular, if you look at the difference between x of omega and E of x given f of omega, this difference will be bounded by the length of this interval, which is 2 over n. this beta must be equal to alpha plus 2 over n by our construction. And this is true for any omega in capital Omega, because this capital Omega is a union of those f sub k's. And remember, we have a covariance laws formula derived above. It immediately follows that this covariance loss is bounded by 4 over n squared in this situation. So what does this tell us? This tells us that given a bounded random variable and given an integer n, there's a way to construct a sub-sigma algebra which is generated by n many sets such that the covariance loss can be controlled by 4 over n squared. And of course, the larger we are allowed to choose the size of the partition of omega, the smaller covariance loss we can get. This is one of the applications of our proposition number 3.